Okay, so atoms are the smallest units of an element, right? Elements are on your periodic table. We'll walk through how to read that again, how to use that, but we're talking about chemistry in relation to biological systems. So for us, there's about 25 elements on the periodic table that are essential to life functioning. Alright? And of those 25 elements, in fact, there's only 4 of them that make up 96% of living things, and that's where we're talking oxygen, carbon, hydrogen, and nitrogen. The other 21 elements that are important to life, we talk about them as trace elements. Okay? Now, that doesn't mean that trace elements aren't important. It's just that they don't make up crazy amounts of matter in living things. Alright? You're going to be responsible for having to know 6 total elements in relation to how they associate with living organisms. The carbon, the oxygen, the nitrogen, and the hydrogen, as well as 2 of the trace elements, your phosphorus and your sulfur. Okay? Alright guys, welcome back. So today we're going to kind of jump into elements and really how those elements are arranged on your periodic table. So remember that your periodic table is this big arrangement of elements in which we put those elements into columns, into rows, and they've all ended up where they are in their position on that table based on a set of properties that repeats row to row to row, which is a really convenient way to utilize that table because it makes it easy for us to start seeing trends, discussing trends, seeing how elements will ultimately then bond and react with each other, which is where we're going post this. So when you look at a periodic table and look at any particular individual block, you should see at least this sort of basic information. So you've got your atomic number, your element symbol, your element name, and atomic mass. Now, depending on the periodic table that you have, you may have more information than this. Every now and again, you'll get a little less, but it really depends on the periodic table that you have in front of you. For you guys, you should have gotten a copy that has pretty much this basic information, and for us, for our purposes right now, that's really all the information that we need. So let's sort of break down and take a look at really what those numbers are useful for. So you've got your atomic number somewhere on your periodic table for each element in the table itself, right? And that atomic number is going to tell you the number of protons that are present in each atom of that element. Remember from before, if I change the number of protons, I change the element. Why? Because ultimately these elements are all arranged in your periodic table based on increasing atomic number, which is an increasing number of protons. Okay? So, that being said, we can also utilize this atomic number, these number of protons, to also predict the number of electrons that should also be present in the element given one particular condition. If I'm talking about an element that's neutral, this holds true, right? Remember, the number of positives in your nucleus, aka the number of protons, has to equal the number of electrons to balance out the positive and negative charges, but that's only if the atom is neutral. If I'm dealing with something like an ion, that won't necessarily hold up, and we'll get more into that in a little while, okay? But for today, let's assume we're talking neutral atoms, so your atomic number is your number of protons, and then that can also be used to predict the number of electrons. The other major number you're going to typically see on your periodic table is atomic mass. Alright? And that atomic mass is the mass of the element itself. And remember, we mentioned yesterday that the majority of your mass is in the nucleus. So what we're really looking at is the number of protons and the number of neutrons. What's the major mass of the element, of the atom, those electrons, while they'll contribute some mass, it's very, very minimal, okay? So typically when you look at a periodic table, you're not looking at whole numbers, right? If I go back to this, right, this is a decimal. Why? Because I'm dealing with atomic mass as opposed to a mass number. So mass number in and of itself is simply the sum of the protons and the neutrons. It really is just the major mass of that particular element. But most of the time it's reported on your periodic table as atomic mass, and that atomic mass is a decimal because it's taking into consideration your isotopes. Now remember we talked about isotopes yesterday as well. Isotopes are the same number of protons because it's the same element, but I change the number of neutrons so that nucleus gets a little heavier or a little lighter based on how many neutrons are there. So it's an average. But there's a little bit more to it than even that. It's a weighted average. And if you've ever heard of a weighted average, it's probably been from things like school grades, right? If your teacher tells you that in this particular course, your tests and quizzes are worth 50% of your grade, your homework's worth 5%, your projects are worth 20%, so on and so forth, they're weighting the average or how much any particular assignment is worth. So those tests and quizzes are going to be given more credit or more worth in that overall average than your 5% for homework. Well, we do the same thing when we make these atomic mass calculations. So if I'm looking at something like these chlorine isotopes down here, alright, chlorine 35 is approximately 76% of the isotopes of chlorine found in nature, where chlorine 37 only makes up about 25, okay, or 24. So that means 75% of the average, 76% of the average is going to go towards this atomic mass, and only 24% of the average is going to go here, alright? So it's not quite just taking your, let's add all these masses up and average them together. It's a weighted average, so keep that in mind. That's part of how you get those really long, big decimals. What are we going to use it for? We're going to use it as a way to estimate the number of neutrons we would expect to see in a standard, typical atom of that element. So how do you do that? Well, typically we're seeing atomic mass reported, not the mass number, but the mass number is really what I need. So if I round my atomic mass to its nearest whole number, subtract the number of protons that I have, which remember, my atomic number tells me that, I can then determine approximately the number of neutrons I would expect to see in an average atom of that particular element. So let's actually do some of that practice. So you've got this table here in your notes, and you should have a periodic table as well. So let's do some. Alright, so each one of you should have a periodic table that looks like this. We're going to try and make sure we use this one just to kind of keep things standard and equal. And let's sort of work through this particular table in your notes, right? So He is helium. So if I come over here to my periodic table, alright, here's my He. Alright, now remember my number of protons is my atomic number. So here's my atomic number at the top, which tells me that I have 2 protons. Alright. For this particular exercise, we're going to assume that the number of electrons is going to balance out those number of protons and that we're dealing with neutral atoms. So if helium's got 2 protons, that means I also need 2 electrons to balance that out. Okay. Now my number of neutrons, I'm going to come back over here and I'm going to take a look at that mass number, or that atomic mass, and round it first. So I've got 4. I'm going to subtract that from my number of protons, which tells me that my number of neutrons is then 2. Okay. the last piece to this is just a little bit of practice with those electron orbitals, right, and the configuration. So I've got two particular electrons in this atom, or this element. And remember, first level can hold up to 2, second can hold up to 8, third can hold up to 8. And for our purposes, we'll stop at the third orbital. You get past that, you get down into some of these transition metals, and some things get a little funky. So we'll leave that for chemistry. Okay. But let's come back over here. So if I've got 2 electrons, I always have to fill the first orbital first. Alright, which means I can put 2 in there. And I've used up all the electrons that I have, and so there won't be any in that second or third. Alright. Let's do one more together, and then I'm going to tell you to pause the video and try to finish up the table and see if you're able to figure this out yourself. So let's try oxygen. So here's my oxygen, right? Protons are my atomic number, so right here, so that tells me I've got 8. Number of electrons, we're assuming these are neutral atoms, so they should be the same number as our protons. My number of neutrons, if I take a look at my atomic mass and round it, I'm going to end up at 16. So 16 minus 8 gets me to 8 neutrons. And if I start filling orbitals, well, I've got 8 total to work with. I got to put 2 in my first orbital. Alright, 8 minus 2 leaves me with 6, which is less than the 8 I'm allowed to put in my second orbital, so we're going to put 6 in there, and that means there's none in that third orbital. Alright, so at this point, do yourself a favor, pause the video, and go ahead and try and figure out what these numbers should be for your Na, which is your sodium, Mg, which is magnesium, and Ar, which is argon. Alright, now that you've tried it yourself, you should have come up with numbers that look like this. So all of your protons should be the same number as your electrons, right, because we're dealing with neutral atoms. Your number of neutrons was your atomic mass, rounded to the nearest whole number. Subtract the number of protons, so for sodium you get 12, magnesium you get 12, argon you get 22. And then we fill your electron orbitals, right? So first orbital can only ever hold 2, so that's where those 2's all come from. Second orbital can never hold more than 8. Third orbital then is where the remaining electrons end up. Alright, some other information about your periodic table. So I mentioned when we started today that your periodic table, those elements are arranged by increasing atomic mass, right? And as we do that, you end up with not only those increasing masses, but those really the proton numbers, and you end up with these trends. And so we've got these rows or periods in your periodic table. For every row, that tells me something about all of the elements in that row. In fact, it tells me how many orbitals they'll have. In each column, it tells me the number of valence electrons, assuming, of course, we skip those transition metals. Alright, and so those number of orbitals and or number of valence electrons, depending on whether I'm talking row or period versus column or group, tells me something about the properties of that particular element, right? So we're all arranged by this increasing atomic number, right, number of protons, and so I get these periods or rows, and everybody in that row has the same number of orbitals. It also ends up putting elements in these groups, assuming I skip these guys, and that's going to tell me the number of valence electrons. So I actually want you to come back to your periodic table, and we're going to label your rows, your periods, your columns, and groups actually on your periodic table itself, so that you have this information to sort of help you out as we're working through some of these problems. So we go down and number your rows first, right? So hydrogen's in row 1, lithium's in row 2, 3, 4, 5, 6, and 7. Alright, and feel free to write somewhere that those numbers tell you the number of orbitals. Okay. If I go across the top then, let's also number these, but now watch before you decide to just jump ahead and do this one. So hydrogen's 1, beryllium's 2, but we're going to skip these transition metals in the center and jump over here to 3, carbon's 4, 5, oxygen's 6, fluorine's 7, and hydrogen's 8. Right? So these tell you your number of valence electrons. Okay? So that's going to be really helpful as we then look at some of the examples. Alright, so you've got this table in your notes. Let's try a couple of these together. I'll also leave you to try some by yourself as well. So first thing I want to do is take a look at my element, right? So sodium's my first one. So if I take a look at my row number, remember rows go side to side. So sodium is right here. Alright, and my row number is 3. Okay. Columns go up and down, so sodium happens to be in column 1. So if I take a look, what does that tell me? Well, remember that your row numbers tell you your number of orbitals. That means a sodium atom has 3 orbitals. Alright, and my column number tells me my number of valence electrons, so sodium has 1. If I come over to carbon, let's try that one together. So carbon's right here, alright, which happens to be row 2. And it's in column number 4. So that means that carbon has 2 orbitals and 4 valence electrons. Now just like before, pause the video, try those last 3 out yourself, and then come back to the video and double check your answers. Alright, so hopefully you got answers that look similar to this. So your row number, right, should always be the same as your number of orbitals, because that's what that particular piece of information on the periodic table tells us. Column number always tells you your number of valence electrons, and so those should also be the same. So if we move on, alright, elements in and of themselves are helpful. We definitely find them in nature. But a lot of times those elements are combined with other elements to make compounds. So when we talk about a compound, still a pure substance just like an element is, meaning if I find that pure substance or that compound anywhere in the universe, properties, composition, it's all going to be the same. It's going to be identical no matter where I find it. But now I'm talking about 2 or more elements that are joined together in some sort of fixed proportion, right? So water, for example, is a compound, always 2 hydrogen atoms plus 1 oxygen atom. Carbon dioxide, always 1 carbon to 2 oxygens. Table salt, sodium chloride, NaCl, 1 sodium to 1 chlorine. Sugar, C6H12O6, same idea, okay? And if I change those elements, or I change the ratio in which those elements are found, then I'm talking about a different compound. For example, CO is not carbon dioxide, it's carbon monoxide. And so its properties are going to be slightly different because the ratio in which I'm finding those elements is different. Something else to keep in mind is that the properties of compounds don't necessarily have any connection to the properties of the elements that combine to make them up. So let's go back to water as an example. If I take elemental hydrogen or elemental oxygen, both of those are gases, naturally. They're also very flammable, and yet I put them together, I now have a liquid, and we use it to put out flames. Same thing with sodium chloride, NaCl. Sodium and chloride in and of themselves also very reactive, very flammable, and yet we stick them together into this compound called table salt, and we use it to salt our food. So we can't necessarily take the properties of a particular element and predict the properties that will be in those compounds. So just something to keep in the back of your head. So compounds we can also talk about as molecules of compounds, right? So the smallest unit of an element is an atom. The smallest functional element or smallest functional particle of a compound is a molecule. Now that being said, I can use that word molecule to talk about compounds, right? A molecule of CO2, a molecule of water. But that word molecule can also get applied to some of these elements that just generally don't get found as a single atom out in nature. In fact, we talk about them typically as diatomic elements, right? Okay, so di meaning two, so O2, N2, so on and so forth. So next thing I want you to try is to go through and let's take a look at this particular table and let's determine, am I talking element, compound, in which case am I talking atom, or then molecule? How do I know that? Well, I've got to take a look at these particular formulas that are going on here in this first column. So just like before, let's do a couple together and then I'll leave you to try a couple and see how you do. So if I take a look at that first one, I've got H2O. Okay, so am I dealing element or compound? Well, by definition, compound is two or more elements joined together, and in this case I've got elemental hydrogen and elemental oxygen in the same molecule, which means I'm dealing with a compound. Okay, and just like that, that throws that term atom out the window. Alright, because atoms are strictly for elements, which means I've got molecules going on here. If I go down to the next one, alright, K or potassium, check out your periodic table. It is an element unto itself, so that's what we're dealing with there. Okay, so not a compound. And in this case, I've only got one K hanging out there, so that means I'm dealing with an atom. Alright, just like before, take a couple minutes, pause the video, try those last couple on your own, and come back to the video, check your answers, see how you did. Alright, so hopefully this is the set of answers that you came up with. Now, for most kids, the sodium chloride, the NaCl, goes really well, compound, so obviously a molecule. Argon they quickly find on the periodic table, so element and atom, this is usually the one that gets kids. Alright, so check this one out. So oxygen, single element, hence why it's here, but this is one of those diatomics, so you got that second number going on. So this is actually a molecule of two oxygen atoms bound together, hence why it's a molecule. So just be careful with that one. Alright, last topic for the day, just a little bit about chemical formulas, right? So we utilize these, and they've shown up multiple times already before in this PowerPoint. We use them to describe the composition of a compound. So compounds are two or more elements, and those elements have to be in a particular ratio to be that particular compound, which means I don't always want to have to say I have one atom of oxygen plus two atoms of hydrogen to tell me that I'm talking about water. I'd rather just write H2O and know what that means. So chemical formulas are our shorthand way of doing that. So I take a look at these chemical formulas. Here are the different elements that are involved, and then those subscripts tell me how many atoms of each that I have. So this particular one, I've got 2 atoms of iron plus 3 atoms of oxygen. So on and so